Okay, everybody. Today we're going to go over just a quick introduction into enthalpy um, and just some things that we need to know about it, define it, um, show you some different things we're going to do with it, and we'll move on to more kind of intricate things involving enthalpy in the following lessons to come. But today's just the, kind of our first introduction into it. All right. So I'm just going to walk you through some notes, explain some things. Hopefully, it'll clear things up for you if you had any issues. All right. So let's go right there. All right. So if we look at the notes handout. All right. So what we're saying is every process, so every chemical change or physical change, it doesn't have to be a chemical reaction. It could just be a physical reaction. So we're talking about vaporizing water. That's a physical change, right? Or we could talk about combustion reactions or redox reactions, chemical reactions. Every single process has a change in what we call enthalpy. All right, now let's define what enthalpy is, and maybe it'll make more sense to you. All right, so first of all, change, remember, mathematically, we represent change with a delta symbol, so that triangle symbol. And H is our symbol for enthalpy. So delta H means change in enthalpy, okay? Now, what enthalpy is, we're going to talk about in more detail to define it. But right now, you can think of H, enthalpy, as just heat. And we're going to show you how it is just heat in a second. Hold on. All right, so sorry about that. My notes are a little bit out of order, so I'm going to scroll down to find the first part of this video because, all right. So hopefully this order will make more sense. Somehow my papers got mixed up when I scanned them. All right, so delta H is enthalpy change or change in enthalpy, okay? Enthalpy equals heat plus the product of pressure and volume, okay? But anytime we are thinking about enthalpy, pressure and volume are going to remain constant. So what does that mean? It means enthalpy for our purposes in chemistry is the same thing as heat. Now, if you go to higher levels of chemistry, and we're talking about beyond first year college chemistry, we're talking beyond, like in organic chemistry, you don't really talk much about enthalpy. It's more of a P-chem thing, a physical chemistry thing. So if you are like a chemistry major and you take P-chem, physical chemistry, like physics, chemistry combined, that's when you'll deal with enthalpy not exactly being the same thing as heat. So enthalpy and heat technically aren't the same thing, but since we're going to leave this constant and that's not going to change, we're going to say the heat and enthalpy are the same thing, okay? So enthalpy is the same thing as heat, but they get two different symbols because technically they aren't the same thing. So H is enthalpy, and when you see Q in equations, like in the Q equals MCAT equation, Q is actual heat. Now, because we're going to say that they're the same thing at all times, that means H and Q are the same thing. So if you saw delta H, which is change in enthalpy, it's really also delta Q. It would be the change in heat as well. It's the same thing. So anytime you see the word heat, you can replace it with the word enthalpy, or vice versa. Anytime you see the word enthalpy, you can change it with the word heat. Okay. If you refer to heat, sometimes like we say the heat of something, you could also call it the enthalpy of something. So let me we'll do this in another lesson, but sometimes we'll refer to the molar heat of formation or the molar heat of vaporization or the molar heat of solution or the molar heat of neutralization or maybe the molar heat of combustion, right? We have all these different little subcategories of enthalpy change. But anytime it's molar heat of formation or heat of formation, you could say enthalpy of formation. Or if you see enthalpy of combustion, it's the same thing as saying heat of combustion. All right, so just you can interchange those words. Enthalpy and heat are the same thing. So when you see H, technically it's enthalpy, not heat, but for our purposes, they're the same thing. So you're good to go. So if you do see H, thinking of it as heat is fine because essentially that's what it is. All right. All right, so now back to the top. So every process, whether it be chemical or physical, has a change in enthalpy. Okay. So if and enthalpy is going to have the units of energy. So joules or kilojoules. Usually, if it's a delta H of a reaction, it's kilojoules, but all that is 1,000 joules. Okay. So remember, when you see negative energy values, all that means is energy was released. So a negative delta H, if you're told whatever change, whatever physical or chemical change that undergoes, if you're told the delta H for that process is negative, then that's telling you that heat is released from the system, but to the surroundings. And remember, your perspective is a perspective of the surroundings. So if you see temperature increase, that means energy is being released from the systems to the surroundings. Okay. So anyway, if you have a negative delta H, that's an exothermic process. Heat's being released by the system. Where does the heat go? It goes to the surroundings. Okay. So vice versa, if you see a positive delta H, that means heat's being absorbed by the system. And where is that heat coming from? It's coming from the surroundings. So the surroundings lose energy to the system if it's a positive delta H. If it's a negative delta H, the surroundings gain energy from the system. All right. But really, negative delta H means exothermic, positive delta H means endothermic process. Okay. So if you're given a chemical equation and they tell you the delta H and it's a negative number, it's exothermic. Doesn't matter what the number is. If it's a really big negative number, like negative 1 million or something, then it's very exothermic, right? If it's a positive number, then it's endothermic, okay? Now, let's kind of talk about what delta means. Delta anything, delta T, delta V, delta whatever, is final minus initial. To find the change in something, you always do final minus initial. And so one way to calculate the delta H of reaction is if you know the enthalpy of the products, that would be the final part of a reaction. And if you know the enthalpy of the reactants, that's the initial part. So products minus reactants is final minus initial. So the enthalpy of the products, and all that, symbol in math means the sum. So you'd have to take the total enthalpy of the products minus the total enthalpy of the reactants. If you do products minus reactants here, that would give you the delta H of an overall reaction. Okay. Okay. So let's talk about what's going on. Okay. So like, how is energy involved? Okay. So remember, heat is just energy. And it's really, the energy due to the motion and vibration of the particles and stuff like that. But let's talk about what's going on here. Okay. So for any change to happen, one way to think about it is the attractive forces of the reactants are broken because the reactants are changing, right? So the reactants are turning into the products. So attractive forces of reactants are broken. So those attractive forces could just be intermolecular forces. If it's a physical change, could just be bonds. It could be kind of a combination, okay? But whatever attractive forces that have to be broken for the change to occur, okay, that requires energy. So the attractive forces of the reactants are broken. That requires energy. So that's a positive energy value, okay? Positive heat, that requires heat, right? That's what that positive H means, right? But at the same time, or not at the same time, it's kind of like, one happens, the other happens, okay? So, but also the attractive forces of the products are formed. So you have attractive forces, intermolecular forces, or bonds, covalent bonds, ionic bonds, all that kind of stuff, right? So you have attractive forces of the reactants being broken, but you have the attractive forces of the products being formed. And when attractive forces are formed, new attractive forces are formed, that releases energy. So that has a negative enthalpy value, all right? So that's releasing energy. So in every single change, there's some processes, some interactions that are being broken that requires energy. There's some interactions that are being formed that releases energy. And whether or not the overall system or the overall change is endothermic or exothermic really depends on these attractive forces, right? Let's think about this. If the attractive forces of the products are stronger than the reactants, what does that mean? It means more energy is released than required. So overall, energy will be released, and it would be exothermic. if the bonds of the reactants, if the intermolecular forces of the reactants are stronger than those of the products, then overall energy would be absorbed, more energy absorbed than released, and so the overall process would end up being endothermic. So a lot of times in a chemical reaction or a physical reaction, you can think of it in terms of the different things that have to happen for the change to occur. So there's going to be different attractive forces that are broken, there's going to be different attractive forces that are formed, but overall, if you know overall heat is released, then that means that the attractive forces formed are stronger than the attractive forces broken. And if overall energy is absorbed for that change to occur, that means the attractive forces broken are stronger than the attractive forces formed, okay? So when you're deciding whether a process will be endothermic or exothermic, well, it depends on the strengths of attractive forces being broken versus the attractive forces formed, okay? So if you have an endothermic reaction, remember, that means the delta H for that process is positive delta H. That means the reactants' attractive forces are stronger than the products, okay? And if you have an exothermic reaction, that means negative delta H. That means the product's attractive forces are stronger than the reactants, okay? So you might not know the individual strengths of all the different forces of attraction versus being formed versus broken, but you know that the net sum of the products is greater than the net sum of the reactants, or vice versa if it was an endothermic reaction, okay? All right, so for a chemical reaction, so this wouldn't be a physical reaction, because remember, in a physical reaction, you're really not breaking chemical bonds, you're not breaking covalent bonds. But in a chemical reaction, you are breaking covalent bonds a lot of times. So bonds are broken and new bonds are formed. So not just IMFs, now we're talking about actual bonds, okay? And so another way to calculate a delta H for a chemical reaction is to do the sum of the bonds broken, that would be a positive delta H, or positive H, minus the bonds formed, that would be a negative delta H, okay? Okay. And so if you do bonds broken minus bonds formed, that's another way to find delta H. Because if this number ends up being bigger, if the bond strength of the reactant or products is bigger than the bond strength of the reactants, the overall thing would be a number minus a bigger number would give you a negative delta H. But if this number is smaller, then a number minus a smaller number is going to end up being positive. So if you're given bond energies, and you want to calculate delta H of reaction, you're going to do bonds broken minus bonds formed. And we'll do an example of that or two in class, but you want to remember, most of the time, 9 times out of 10, when you're doing delta, right, delta anything, it's final minus initial, just like I brought up earlier in this video. But here's a case where it's actually kind of initial minus, it's reactants minus products instead. But that's because bond energies are always reported as the amount of energy required to break the bond. And we got to flip the sign of that for the bonds of the products because energy is being released. So another way to do it, you could still do products minus reactants if you wanted to using bond energies, but you would have to make the bonds of the products negative numbers. Here, we're making it a negative number by just subtracting, okay? All right, so anyway, another key concept about enthalpy is if the forward process releases energy, the reverse process does the opposite, okay? So if the forward reaction is exothermic, the reverse reaction is endothermic. And so here we have a simple, here we show water freezing, that we already know that's an exothermic phase change. That releases this much energy per mole of water, okay? Well, that means the reverse process, all I did was flip the reaction. If I flip the reaction, what happens? I flip the sign of delta H. So to melt that much water would require the same amount of energy, okay? But it would be a positive energy value now because it's required. It's being absorbed by the ice to melt. But here, as the water freezes, that much energy is being released to the surroundings, Okay, so what does that mean? It means if you flip a reaction, if you write the reverse of a reaction, you flip the sign of delta H. Okay, so if it was exothermic, now it's endothermic. If it was endothermic, now it's exothermic. Okay. All right. So that was their first page. All right. So what I want you to notice is a lot of times you're given this unit for a delta H of reaction. It says kilojoules per mole of reaction, RXN. So if this is my reaction, a way to think about it is if you put kind of parentheses around the whole reaction, the whole balanced equation, and put a 1 outside of it, this would be 1 mole of the reaction. So the way to interpret it, 1 mole of this reaction consumes 2 moles of benzene, 15 moles of oxygen, 12 moles of CO2, and 6 moles of water, okay? And 1 mole of the reaction produces this much energy. And I said produced because delta H is negative. So energy is released, energy is produced, okay? So we know just looking at the delta H, this is an exothermic process. We know energy is released. But we also can use the delta H value, because it's per mole of reaction, with ratio, in our ratio with our coefficients of our balanced equation. So again, 1 mole of that above reaction consumes, 1 mole of this reaction consumes 2 moles of this, 15 moles of this, but it would produce 12 moles of CO2, 6 moles of water, and that much energy, okay? So different ratios you can make with delta H from that equation. I didn't include all of them, but you could say that much energy for every 2 moles of benzene consumed. You could say that much energy for every 15 moles of oxygen consumed. You could say that much energy for every 12 moles of CO2, and you could flip these ratios. You could do 12 moles over that much energy, 15 moles of oxygen over that much energy, and you could include the water too. You could say this much energy for every 6 moles of water, okay? So that means we can do stoichiometry with delta H. So like we're still using that above equation. If you were asked this question, what mass of water is produced when 8,000 kilojoules of energy is released from the above reaction? So we were given how much energy is produced, and we wanted to know how much water was also produced. And notice that I really didn't need that negative sign here, because I said how when this much energy is released. So the word released makes this a negative 8,000. So I don't need the negative sign there. It's kind of redundant, okay? But you know, this is basic stoichiometry. So we would take our energy given, and we would figure out the ratio to convert moles of water, for energy to moles of water. Well, that ratio is given to us in this balanced equation. Whoops, okay? This much energy for every 6 moles of water. So 6 moles of water for every that much energy. So we have our ratio, 6 moles of water for every 2,500 kilojoules. I don't need the negatives, okay? So kilojoules cancel out, that would give me moles of water, and then I multiply by the molar mass, and that would give me how many grams, okay? But what we want to understand is, if we double a reaction, we double the delta H. So this is just showing the vaporization of water, and this is how much energy it takes. But what if it was this? What if it was 2 moles of water? Well, all I have to do is double the delta H value. So if I double the equation, I double the delta H. If I quadruple an equation, I quadruple the delta H. It's pretty easy. Now, what would this reaction be? Okay, so now we notice that this reaction is basically this reaction, but it's flipped, and it's 1/2. So what would we do with the delta H? Well, we flip the reaction, so we would make this negative, and then we halved the coefficients, so we would half this value. So the delta H for this reaction would be negative 40.7 divided by 2. All right, so the delta H of that would be just negative 40.7 divided by 2. Okay. All right, so hopefully that kind of straightened things out a little bit about delta H, but we're going to get into a lot more details about enthalpy change and stuff in class and moving forward, and I'll post a couple of other videos this week doing more with delta H of reactions. And what we're going to end up leading to is specific types of reactions. So there's going to be, you're going to see delta H's with different subscripts. And those different subscripts describe a specific process. So a specific type of chemical or physical reaction. All right, and then those are things that you could like look up and use and apply in other scenarios. All right, so that's it. So hopefully that makes sense to you. Sorry, my notes weren't in order. That's upsetting to me. But anyway, hopefully not upsetting to you. Have a great day, and I'll see you in class later.